Okay, so on the continuing notes from continuity, the lesson on continuity, we have a different f of x here where we have the square root of x squared plus x minus 6. Now we know those have to be positive values because it's a radical, so all we know is that x squared plus x minus 6 must be greater than or equal to 0. That just means, what does that mean? Greater than or equal to 0. Ensures it's positive because we don't want a negative under there. We get into imaginary stuff. So all we're saying is we know that must be positive. So we're going to factor it so we can look at the values. What multiplies to give us negative 6 adds to give us positive 1. Good. Which means negative 3 and positive 2 when you set those equal. That's the values that we're going to be looking at and working with. So we know things happen there. So let me come over here and I want to look at negative 3 and positive 2. Make sure and put them in order of the number line, okay? So whatever you get there. Now, we have to test this to figure it out. This one's just not intuitive and not just right off the mark. We actually have to test these intervals when we have them. So I'm just going to pick, let me call this test. And I'm going to pick a value to the left of negative 3. So I'm going to pick test negative 4. I can pick any number to the left of my negative 3 and try it out. Okay? So I'm just going to come down here and say test x equals negative 4. Everywhere that there's an x, I want to plug in
I have a question.
negative 4 and see if it's greater than or equal to 0.
So x has to be greater than or equal to 0, or the problem.
The values that we have in there, and that's what we're testing. You can see I'm going to plug it into the whole function, and I'm trying to see, will my answer here be greater than or equal to 0? And we're going to individually test each one. Just our points in which we're going to test are going to be these ones that we found, the factors. So we're going to test to the left of them, to the right of them, because we know that's where things happen, right? So 16 square root of 6. Square root of 6 is greater than or equal to 0, so this is true. It's positive. It's true. So if that's true, I'm going to shade it.
So for our testing values, like you want us to put those at the top too, so you know what we're using.
I'm just doing it, color coding it, but if you come over here and clearly say this, I should be able to look up there.
Okay.
But yeah, especially on a test, you should, if you label, the more work you show, the more chance you are to get partial credit. All right, so I'm going to test this next interval. Our favorite one to test is in between a negative and a positive is always 0 because it's probably very easy. So I would just plug 0 in. 0 squared plus 0 minus 6. So that's the square root of a negative 6, which is not. So this is false. So I'm not going to shade that region up there. It's false. Meaning any value I put in that I would pick right here, any value in here that I would pick and plug in here, I'm going to get a false value. So you don't include it. All right? And we're going to test one more part of the interval. I'm going to test to the right. I'm just going to pick positive 3. You can pick anything. You don't have to pick the same ones as me. Just pick some value in that interval. So that would be 3 squared plus 3 minus 6. And I want to know, is that one greater than or equal to 0? So 9 plus 3 is 12 minus 6 is square root of 6. That is true. Therefore, I want to shade that. Okay, we will include those. Those will be closed circles because at those points is where we get the 0, right? But what is the square root of 0? 0, so that's okay. So the 0 part gets to be included. That means the zeros are included, so put a closed circle. Now, what's continuous? How would we name that? Negative infinity to 3 with a bracket. Bracket because it's a closed circle this time. So we would say continuous from negative infinity to negative 3 bracket union bracket 2 to infinity. So if you have a radical, it's a little bit different. We literally have to find where it's equal to 0 and check that, and then we have to test intervals. Now you have freedom to pick your test values, but if it's going to hold either true or false. The true ones you will include in your graph, and it's where it's continuous. The false ones you don't. Okay. This next one, now this is what you're going to see because I gave you a printout, and just to save time on graph, this is what your problem will look like, minus this left and right. Okay. Let me take that off. So that wouldn't be there either. Okay. What happens is I'm visually, I'm looking at this thing, one I could graph. It's a piecewise function. It means if x is less than or equal to 1, this is what your graph should look like. Less than or equal to 1, where is that on the number line? To the left, right? What is greater than 1? To the right. So I'm going to add in to myself a little side note. This is my left. This is my right side. Because this is a piecewise function. Now, let me do, since it looks like I have this thing color-coded, let's do the blue is the left and the green is the right. So if you graph this, that's what it looked like. My function 3 minus x is right here. And this cubic function is this, but it says only you include the blue one if it's less than or equal to 1. So here's my 1. I'm only going to include this part of it. This part says graph this, but all you care about is the portion of that graph where x is greater than 1. So right here, greater than 1. So really, you need to visually only see color. I wanted you to see the rest of it so you know where it came from. You weren't provided that graph. You will have to do that. That's what a piecewise function looks like, and that's how it's derived. So all you really see is color when I ask these questions. Now it's saying, find the limit of f of x. Me, I'm going to look at it from the left. I'm going to look at it from the right. I'm going to look at the limit of the function, right? So I look at it from the left. So I'm approaching the limit from the left. What is that? Which, now let's go ahead and take this one step further, and I'll say the limit. Which one of those describes the left bound? We already labeled it. Blue. The blue one, so I would say x cubed. So that I know I'm only looking at that. One from the left. What is that? What's the limit as x approaches 1? 1. Good. All right. The limit as x approaches 1 from the right means I'm grabbing, what's my function?
3 minus x.
Good. All right. Now, evaluate that, and let me put it in green. So what about the limit of the function, limit of f of x? Is that you guys are so smart already. Okay. So when you see your example, your function, you're given a piecewise function and it says evaluate the limit, that's what you're doing. And a couple of things, the stuff in color, that's what I'm thinking, okay? I'm thinking out loud to you. Less than or equal to 1, oh, that's the one I'm looking at from the left. Greater than or equal to 1, that's the right side. And so if you're a visual person, sketch it out, okay? If you're an algebraic person, however you want to go about that. Okay, oh, wait. So, the other thing we can know about this, all right? Pretend I didn't show you this yet, right? Where would that thing be discontinuous at? If you're given a piecewise function, where is it discontinuous? Look at your equation, what's given.
0.
No, what's the number? 1. At 1, something's happening, right? Because the bounds is defined. It's saying, oh, I want you to look to the left of 1, or I want you to look to the right of 1, aka that means something's happening at 1. And if it's two different functions, more than likely it's discontinuous there. So when we see a piecewise like this, and it's giving you descriptions, look to the left of 1, look to the right of 1, that's because that thing's broken at 1. Meaning, what's that mean? What's that mean? Discontinuous at 1, right? So this means so what if I ask you, where is this function continuous? Because you will have one on your test like this as well. I'll give you a piecewise function, and I'll say, where is this function continuous?
Negative infinity to 1.
Good.
Thing 1 to infinity.
So we would say continuous, negative infinity to 1, parenthesis, 1 to infinity. All right. I know you've done intermediate value theorem before in pre-cal at some point, but we're going to revisit this for a second. If f is a continuous function on a closed interval from a to b, so here's my function f, and it's saying you're on an interval from a to b, okay? If k is any number between there, between f of a and f of b, then there's at least one number c in that interval such that f of c equals k. All right. All it's saying is if you're given a, we're going to break this down. If you're given a, that's our x value, or b, and b, I evaluate f of a. I plug it in to get the y value, right? And then I do the same thing, f of b. I plug it in. If there is a number in between two of these such that we can know the value of c, and it must be in that interval. Okay? So let's look at an example. It's like, well, what does that mean? How do we do that? Also, the easier idea about that is, I think in pre-cal you did more so along the lines, and we'll have a problem like this. If you evaluate f of a, and you got a negative number, and you evaluated f of b, and you got a positive number, that means positive number. That means at some point you went from negative value to a positive value that guarantees that you crossed the x-axis and had a 0. That's the part that you talked about in pre-cal. It's intermediate value theorem, but we used it for zeros. Now we're going to say find c where that happens. So hopefully you remember a little bit about that in pre-cal, but if not, we'll cover what we need to know here. So your question is, with intermediate value theorem in mind, and IVT stands for that, verify intermediate value theorem for f on that interval a to b by showing that if I can know f of a and I evaluate f of b and I know k is in the middle of them, then there's some value c that we can find such that f of c is equal to k for something in the interval a to b. All right? Now, let's break that down. They give us a function, and they give us an interval to look at. All right? This is our a and b. The first thing we got to do is figure out, well, what is f of a? Which f of a is a is -1, so it's saying evaluate, which that means f of -1. So we want to go to the function f, x cubed plus 1, and plug in what? -1. And that's just going to give us 0. The next thing we need to do is to evaluate f of b. B is 2, so that means evaluate f of 2. Write my function down everywhere that there's an x, plug in 2. 2 cubed is 8 plus 1 is 9. Alright, do all your scratch work. We have f of A, we have f of B. F of C, what would f of C be? Anybody? Careful. The function evaluated when x is C. So everywhere there's an x, plug in a C. So what would it be? Close. C cubed plus 1. All this is saying is go to your C function, go to your f of x function, plug in a C everywhere there's an x, so plug in a C right there. Now, we just didn't know the value of C, so we don't have a number value there like we did because we knew A and B. C we don't, so we have to leave it with a variable in there. So you just have f of C would be C cubed plus 1. Now, I calculated work on all that other stuff. The other thing I'm going to look at is it'll say, right here I have f of A is less than or equal to K is less than or equal to f of B. Well, I evaluated this one, so 0. So I know that K, you see this right here? That K is going to be somewhere between 0 and 9 because it's in between them. That's one of the things we need to establish there. But we're not done. What's the next thing it asks us?
You have to plug in C.
We have
plus 1 for K.
We have this right here that we haven't used yet, right? So I have f of C is equal to K. Well, f of C is C cubed plus 1. I need to find out what is C. What value of C makes that true? So I need to find C. What's the first thing I need to do to get C by itself? Subtract 1. Subtract 1, good. So find C. And then do what? Take the cubic root of that, whatever you do to one side, do to the other. So C is equal to K minus 1. Now, this particular, we have a formula or we have a relationship for finding C. In respect, that's what's given. Using intermediate value theorem, and we know where K can possibly lie. K lies between 0 and 9, and it arrow backs over, so we can find, depending on what values they give us. So it'll say find C, what's some C that this theorem holds true. So they're going to be, that's one type of way that you may be asked to use it. Another type of way is we're going to look at this next one. Verify intermediate value theorem applies. Find the value of C. So this time, find the value of C. It didn't say describe the point at which C makes this theorem true.
So what was the answer?
That square root, cube root of x minus 1. Yeah. They would have to give us more information for us to give us more. They said find the relationship of C, the value of C that would make that relationship true. Here, it's a little bit different because they gave us our function. What is this? They gave us our interval, and this time they told us f of C equals 0, so they gave us information about C this time that we didn't have last time. So we have a little bit more information, and you'll see. So just like before, the first thing you want to do is, we know this thing is a polynomial function, so it's continuous everywhere, and for sure, continuous on the interval from 0 to 3. We're only looking at that part, so you want to know it's continuous. I'm just going to make this note, f is continuous. So some things that I'm looking at. The next thing I'm going to do is what? F of A, F of B, collect your data. Okay, we know we need for intermediate value theorem, we know F of A. So F of A means What's our A in this one? And what's our B? 3. So let's do f of A, which would be f of 0. 0 squared. You don't have to do zeros, but I'm going to plug it in just so you have a paper trail. And we get 8. F of B would be f evaluated at 3 in this case. So 3 squared minus 6 times 3. -1. All right. F of C would be C squared minus 6C plus 8.
It says F of C is 0.
Yep, we're going to work with that. But I'm still, each time I'll calculate f of C, now I can plug in a value for that. All right, but because we know that f of C equals 0 from right here, I can set that. I'm going to come over here and say C squared minus 6C plus 8 equals 0. And now I can solve for C. So factor, what multiplies to give us 8, but when we add, we get -6, so that would be C minus 4. C minus 2, right? Because you get positive 8. Negative times a negative is a positive. When I add them, I get -6. So C is equal to 4. C is equal to 2. Now, that's the values for C that's true, but what about only one of those answers count? And I need you to tell me why.
It has to be 2 because it's continuous from 0 to 3.
It has to be in the interval that they ask us about.
And it falls in between.
It falls between 0, so you have to, after you get your values for C, you have to go back to the original problem and check the interval that's in question. So we would say C is equal to 2, and our note is that
Okay, I have a question. I actually have 2 questions. So did you find A and B just because that's where you're supposed to start?
yeah, well, most of the time I'm just going to always calculate A and B because I want to see that, and I know that C is a 0, but technically we didn't. C is 2, and it's in between there. Also, it's a 0 as well because if you had -1 and a positive, I know that has 0. It's anytime I have intermediate value theorem, by nature, I'm just going to do that. It tells you some stuff about it. Didn't necessarily have to use it a whole lot, but it's good habit. Yeah.
Okay, and on the one before that, I didn't want to stop you. But you know how it said K was equal to F of C? Okay, could you just plug in C cubed plus 1 where K is? And then evaluate
I'll
that?
plug in a K right there. Yeah. Like
'Cause
right
you would
here.
get 2 if
So
you did
put
it.
in a K right there. That's kind of what we did. I just moved it over there. But like we did over here, you can plug in K right there. You still have -1, still the cube
But
root.
we didn't find the actual answer because it didn't ask for it.
Right,
Right?
right. Because the wording was for some C. Some C, we would need more information to give them the exact C. If they gave us some K, we could tell them what C was.
Yes, ma'am.
Okay. So it's just the most general form
Yes, ma'am.
there. All right. Use this to determine. Now this is what we did in pre-cal. This is saying use IVT to show that the polynomial function given has a 0. To guarantee that it has a 0, all we have to do is evaluate just like we did a minute ago. So by habit and by nature, any intermediate value theorem, I usually look at f of A and f of B just because it tells us information about it. So I'm going to start there. So let's do f of a, what's our a this time?
0.
And our b is 1. So f of 0 would be f of b is f of 1. So 1 cubed plus 2 top. So if I'm evaluating a function, and when I evaluate f of a I got -1. F of b I got +2. So if I'm going from a to b, does that guarantee that we cross 0 at some point? Yes. So what's the thing, without me drawing an image of that, what's the thing that you're looking for? If this goes from negative to positive or from positive to negative, you know there has to be a 0. It had to cross the x-axis at some point. Now, what if we had f of a was -5 and f of b was -8? You would say no 0, only because of the sign change. So f of a and f of b, with intermediate value theorem in mind, tells us that kind of information. All right? So here we would say, the nice way to put it is f of 0 is less than 0. F of 1 is greater than 0. Therefore, there must be some c in the interval 0 to 1, in the interval a to b, such that f evaluated at c is equal to 0. All right. Now I'm just going to we're just going to do a little bit of review, throw some different stuff at you, look at just evaluation limits. It's just some things you might see in homework. So, if I say, here's your limit of your function, what is as x approaches 8 to the right? Now, I'm not going to draw it. I want you to algebraically kind of in your mind do that. First of all, plug in an 8. What do you get? Definitely not an indeterminate form, so we're good there. Your answer is going to be 1/16. Now, when we check to the right of it, like I could do 8.01. I could even be like 8.001. Or I can even pick 8.0001 if I wanted to get very close to it. But the limit says we want to know what's happening to that function as it gets really close to it, right? So it's sufficient enough. 1/16, we know what's happening. It's pretty clear. What about the next one? 5 from the right. But first of all, if I was to just plug in regular 5, we would need to do a little more work, right? Because we would get indeterminate form. So let's just real quick. X minus 5. Difference of squares on the bottom. What's that guy called? What's that called?
Removable discontinuity.
Removable discontinuity. Good. So then it allows us to still evaluate the limit as x approaches 5 from the right. What happens if we put a 5 in there? 1/10. And 5 to the right of that, a little bit to the right, it's going to be just, it doesn't change anything. We just have 1/10. All right, you guys are getting good at this. How do you feel about that?
Oh, yeah, baby.
All right, I want you to talk to me. So don't say anything out loud just yet. So we give everybody just a minute. It's a limit. I tell you the function is piecewise. So we're going to look at the limit from the left. The limit of f of x is x approaches 3 from the left. You were missing one?
I'm sorry.
There you go. We're on this one. It's on the back of that. All right, so here we go. Talk to me about anything that you see. Just share your thoughts when you see that. Something's going to happen at 3. Perfect. Good. So something's happening at the 3 because they're telling us, they're saying, look at this thing. Especially we want to look at it to the left of 3 and to the right of 3. So discontinuous at 3, right? What if I were to ask you, where is this function continuous? Where would you tell me?
Negative infinity to 3, union 3 to infinity.
So smart. Y'all make me so proud. All right. Now, which one's the left function and which one's the right? So visually, I'll know what I'm working with.
Top one's the left, the bottom one's the right.
So which one am I going to work with?
Top.
Yes. You see it? Okay, good. Yes.
Going back a couple pages when you had first show piecewise function, we wrote out the continuum, we did put the bracket.
You have a bracket that was equal to.
Yeah, only if it's equal to, but it's discontinuous at those points. We use bracket on the square root one because it can be greater than positive there, and our zeros were positive.
We said less than
Where's that?
right there.
Less than or equal to. Well, at that point, that one is, but the other one's not. So the function itself as a whole, because look at it, it's still discontinuous. That's a good question now. I see where you're saying. So she was asking, and it's a legitimate thing. She's like, well, because this is or equal to, so at that one, we will have on the cube one, this one will be closed and that one needs to be open. So yeah, so let's fix, so we'll have this one, with the blue one we said is closed, and the green one's going to be open, so which one of those gets the bracket?
First one.
The first. Good question, good catch there. Okay, so here we are, we're back here. And so we're going to evaluate the one that's to the left, which we said was the limit. Let me put this in a different color. Let's go blue. The limit of x plus 2 over 2, because we're looking at the one from the left. Now plug it in and what do we get? 3 plus 2 is 5 over 2. Okay? Alright, next one, the limit of f of x, where f of x is another piecewise function. We're looking to the left of 3, to the right of 3. So it said, what is the limit of this function as x approaches 3? So talk to me.
You have to use the bottom one because it's equal to.
We actually have to look at it from the left and from the right to determine the f of x itself, right? So we're going to do both. We're going to look at it from the left, evaluate it. We're going to look at it from the right, evaluate it. And then what about those two? If they're not this, they have to be the same. And then we say the limit exists, and the limit of f of x exists. So let's do this. So do limit. The top one, x squared minus 4x plus 6, is which one? The left or the right? The left, because it's saying x is less than or equal to 3, so we're looking on the left side of it. So this one will say at 3 from the left. do negative x squared plus 4x minus 2, but I'm going to look at it from the right, because that's where it's greater than or equal to 3. So limit from the left, limit from the right. So what does that tell us about our limit of f of x? As x approaches 3. All right. Find the x values, if any, at which f is not continuous. Which discontinuities are removable? So first of all, what's the first thing wanting us to do? Find where it's discontinuous. So what do? We take the denominator, set it equal to 0, we factor it to know where that happens. So it's, if I was to factor that, it would be x minus 3, x plus 2. So x cannot equal 3 and x cannot equal negative 2. So it's discontinuous here. But it says, see if something's removable. So we're going to take our original and write it over the factor form, which was x minus 3, x plus 2. Right? And then what? So our removable discontinuity, so we would say removable at x plus 2 or x equals negative 2. Right? That's the same thing. Removable discontinuity at x equals negative 2. I'm just going to define it that way because that makes more sense. At x equals negative 2. So that's where it's removable. So let's evaluate the limit. Limit of f of x. So we'll have 1 over x minus 3 as x approaches at negative 2. Since it's removable at negative 2. So evaluate the limit there. 1 over negative 2 minus 1. Or negative 1/5. We have a non-removable at what? 3. X equals 3. Good. So when you're given a function, if you can factor it and something cancels, that's a removable discontinuity. If not, it's called a non-removable. You can evaluate the function, the limit of the function, at that removable continuity and still evaluate your function. If you were to plug in negative 2 in the beginning, it would have given you 0 over 0, which would have been indeterminate form. Okay? So, just some terminology there. Oh, we didn't talk about continuous. What if I said, where is it continuous? It didn't ask that, but if I were to ask you, we would say, put these in order. To negative 2, union 3 to infinity. Good. So, the mindset is on your test, it's going to ask continuous. But we know we got to find discontinuous first to then do that part. All right. Now, this is also the one that it'll have one like this on your test. Use the definition of continuity to show that your function is continuous at point x equals 3 when your function is given. F of x is equal to negative x squared plus 4x minus 2. Tell me the 3 conditions that must apply that you're going to have to write out on your test. F of c must exist. It must be it's defined and it must exist, okay? What's the next one? The limit as x approaches c, or in this case 3, must exist. And then what about these two? They have to equal each other. So that's our 3 conditions. So now we're going to show that, right? So earlier in your test, you gave me the definition. Now when it says use the definition, this is what it's going to look like. So I'm just going to label it like part 1, f of 3. So when x is 3, I'll plug that into my function. And I'll get negative x squared plus 4x minus 2. Everywhere that there's an x, plug in 3. I evaluate that and I get 1. Alright, and then my next thing, so f of c is defined, it exists, got an answer, good. The next thing I want to know is, does the limit of this function as x approaches 3, what about it? So we're going to take that function, everywhere there's an x, plug in 3. So, which is what we just did, right? So, part 3 says f of 3 is equal to the limit of f of x as x approaches 3. Therefore, because part 1, the function f of c is defined. Part 2, the limit of f of x as x approaches c exists. And these two are equal to one another. That's the third part of it. We know it's continuous at that point. Okay, so on your test, when I say use the definition of continuity to show it's continuous, this is exactly what you're going to do. Okay.